Injection molding.
Injection molding is a manufacturing process for producing parts by injecting material into a mold. Injection molding can be performed with a host of materials, including metals, glasses, elastomers, confections, and most commonly thermoplastic and thermosetting polymers. Material for the part is fed into a heated barrel, mixed, and forced into a mold cavity where it cools and hardens to the configuration of the cavity 240 after a product is designed, usually by an industrial designer or an engineer. Molds are made by a mold maker from metal, usually either steel or aluminum, and precision machined to form the features of the desired part. Injection molding is widely used for manufacturing a variety of parts, from the smallest components to entire body panels of cars. Parts to be injection molded must be very carefully designed to facilitate the molding process. The material used for the part, the desired shape and features of the part, the material of the mold, and the properties of the molding machine must all be taken into account. The versatility of injection molding is facilitated by this breadth of design considerations and possibilities.
Applications.
Injection molding is used to create many things such as wire spools, packaging, bottle caps, automotive dashboards, pocket combs, some musical instruments, and parts of them, one-piece chairs and small tables, storage containers, mechanical parts, including gears, and most other plastic products available today. Injection molding is the most common modern method of part manufacturing. It is ideal for producing high volumes of the same object.
Process characteristics.
Injection molding utilizes a ram or screw-type plunger to force molten plastic material into a mold cavity. This solidifies into a shape that is conformed to the contour of the mold. It is most commonly used to process both thermoplastic and thermosetting polymers, with the former being considerably more prolific in terms of annual material volumes processed. 1 to 3 thermoplastics are prevalent due to characteristics which make them highly suitable for injection molding, such as the ease with which they may be recycled, their versatility allowing them to be used in a wide variety of applications, 8 to 9, and their ability to soften and flow upon heating. Thermoplastics also have an element of safety over thermosets. If a thermosetting polymer is not ejected from the injection barrel in a timely manner, chemical cross-linking may occur, causing the screw and check valves to seize and potentially damaging the injection molding machine. 3. Injection molding consists of high-pressure injection of the raw material into a mold which shapes the polymer into the desired shape. 14 molds can be of a single cavity or multiple cavities. In multiple cavity molds, each cavity can be identical and form the same parts, or can be unique and form multiple different geometries during a single cycle. Molds are generally made from tool steels, but stainless steels and aluminum molds are suitable for certain applications. Aluminum molds typically are ill-suited for high-volume production or parts with narrow dimensional tolerances, as they have inferior mechanical properties and are more prone to wear, damage, and deformation during the injection and clamping cycles. But are cost-effective in low-volume applications as mold fabrication costs and time are considerably reduced. Many steel molds are designed to process well over 1 million parts during their lifetime and can cost hundreds of thousands of dollars to fabricate. When thermoplastics are molded, typically pelletized raw material is fed through a hopper into a heated barrel with a reciprocating screw. Upon entrance to the barrel, the thermal energy increases and the van der Waals forces that resist relative flow of individual chains are weakened as a result of increased space between molecules at higher thermal energy states. This reduces its viscosity, which enables the polymer to flow with the driving force of the injection unit. The screw delivers the raw material forward, mixes and homogenizes the thermal and viscous distributions of the polymer, and reduces the required heating time by mechanically shearing the material and adding a significant amount of frictional heating to the polymer. The material feeds forward through a check valve and collects at the front of the screw into a volume known as a shot. A shot is the volume of material that is used to fill the mold cavity, compensate for shrinkage, and provide a cushion, approximately 10% of the total shot volume, which remains in the barrel and prevents the screw from bottoming out. to transfer pressure from the screw to the mold cavity. When enough material has gathered, the material is forced at high pressure and velocity into the part-forming cavity. To prevent spikes in pressure, the process normally utilizes a transfer position corresponding to a 95 to 98% full cavity where the screw shifts from a constant velocity to a constant pressure control. Often injection times are well under 1 second. Once the screw reaches the transfer position, the packing pressure is applied, which completes mold filling and compensates for thermal shrinkage, which is quite high for thermoplastics relative to many other materials. The packing pressure is applied until the gate, cavity entrance, solidifies. Due to its small size, the gate is normally the first place to solidify through its entire thickness 16. Once the gate solidifies, no more material can enter the cavity. Accordingly, the screw reciprocates and acquires material for the next cycle while the material within the mold cools so that it can be ejected and be dimensionally stable. This cooling duration is dramatically reduced by the use of cooling lines circulating water or oil from a thermolator. Once the required temperature has been achieved, the mold opens and an array of pins, sleeves, strippers, etc. are driven forward to demold the article. Then, the mold closes and the process is repeated. For thermosets, typically 2 different chemical components are injected into the barrel. These components immediately begin irreversible chemical reactions which eventually cross-links the material into a single connected network of molecules. As the chemical reaction occurs, the 2 fluid components permanently transform into a viscoelastic solid. Solidification in the injection barrel and screw can be problematic and have financial repercussions. Therefore, minimizing the thermoset curing within the barrel is vital. This typically means that the residence time and temperature of the chemical precursors are minimized in the injection unit. The residence time can be reduced by minimizing the barrel's volume capacity and by maximizing the cycle times. These factors have led to the use of a thermally isolated, cold injection unit that injects the reacting chemicals into a thermally isolated hot mold, which increases the rate of chemical reactions and results in shorter time required to achieve a solidified thermoset component. After the part has solidified, valves close to isolate the injection system and chemical precursors, and the mold opens to eject the molded parts. Then, the mold closes and the process repeats. A parting line, sprue, gate marks, and ejector pin marks are usually present on the final part. 98. None of these features are typically desired, but are unavoidable due to the nature of the process. Gate marks occur at the gate which joins the melt delivery channels, sprue and runner, to the part-forming cavity. Parting line and ejector pin marks result from minute misalignments, where, gaseous vents, clearances for adjacent parts in relative motion, and/or dimensional differences of the mating surfaces contacting the injected polymer. Dimensional differences can be attributed to non-uniform, pressure-induced deformation during injection, machining tolerances, and non-uniform thermal expansion and contraction of mold components, which experience rapid cycling during the injection, packing, cooling, and ejection phases of the process. Mold components are often designed with materials of various coefficients of thermal expansion. These factors cannot be simultaneously accounted for without astronomical increases in the cost of design, fabrication, processing, and quality monitoring. The skillful mold and part designer will position these aesthetic detriments in hidden areas if feasible.
History.
In 1847 Johns Jacob Berzelius produced the first condensation polymer, polyester, from glycerin, propentriol, and tartaric acid. Berzelius is also credited with originating the chemical terms catalysis, polymer, isomer, and allotrope, although his original definitions differ dramatically from modern usage. For example, he coined the term polymer in 1833 to describe organic compounds which shared identical empirical formulas but which differed in overall molecular weight, the larger of the compounds being described as polymers of the smallest. According to this, now obsolete, definition, glucose, C6H12O6, would be a polymer of formaldehyde, CH2O. The first man-made commercial plastic was invented in Britain in 1861 by Alexander Parkes. He publicly demonstrated it at the 1862 International Exhibition in London, calling the material he produced Parkesine. Derived from cellulose, Parkesine could be heated, molded, and retain its shape when cooled. It was, however, expensive to produce, prone to cracking, and highly flammable. In 1868, American inventor John Wesley Hyatt developed a plastic material he named celluloid, improving on Parkes' invention so that it could be processed into finished form. Together with his brother Isaiah, Hyatt patented the first injection molding machine in 1872. This machine was relatively simple compared to machines in use today. It worked like a large hypodermic needle, using a plunger to inject plastic through a heated cylinder into a mold. The industry progressed slowly over the years, producing products such as collar stays, buttons, and hair combs. The industry expanded rapidly in the 1940s because World War II created a huge demand for inexpensive, mass-produced products. In 1946, American inventor James Watson Hendry built the first screw injection machine, which allowed much more precise control over the speed of injection and the quality of articles produced. This machine also allowed material to be mixed before injection, so that colored or recycled plastic could be added to virgin material and mixed thoroughly before being injected. Today screw injection machines account for the vast majority of all injection machines. In the 1970s, Hendry went on to develop the first gas-assisted injection molding process, which permitted the production of complex, hollow articles that cooled quickly. This greatly improved design flexibility as well as the strength and finish of manufactured parts while reducing production time, cost, weight and waste. The plastic injection molding industry has evolved over the years from producing combs and buttons to producing a vast array of products for many industries including automotive, medical, aerospace, consumer products, toys, plumbing, packaging, and construction 1–2.
Examples of polymers best suited for the process.
Most polymers, sometimes referred to as resins, may be used, including all thermoplastics, some thermosets, and some elastomers. Since 1995, the total amount of available materials for injection molding has increased at a rate of 750 per year. There were approximately 18,000 materials available when that trend began. Available materials include alloys or blends of previously developed materials, so product designers can choose the material with the best set of properties from a vast selection. Major criteria for selection of a material are the strength and function required for the final part, as well as the cost, but also each material has different parameters for molding that must be taken into account. 6 common polymers like epoxy and phenolic are examples of thermosetting plastics, while nylon, polyethylene, and polystyrene are thermoplastic. 242. Until comparatively recently, plastic springs were not possible, but advances in polymer properties make them quite practical. Among such applications are buckles for anchoring and disconnecting outdoor equipment webbing.
Equipment.
Injection molding machines consist of a material hopper, an injection ram or screw-type plunger, and a heating unit. 240. Also known as presses, they hold the molds in which the components are shaped. Presses are rated by tonnage, which expresses the amount of clamping force that the machine can exert. This force keeps the mold closed during the injection process. Tonnage can vary from less than 5 tons to over 9,000 tons, with the higher figures used in comparatively few manufacturing operations. The total clamp force needed is determined by the projected area of the part being molded. This projected area is multiplied by a clamp force of from 1.8 to 7.2 tons for each square centimeter of the projected areas. As a rule of thumb, 4 or 5 tons per inch can be used for most products. If the plastic material is very stiff, it will require more injection pressure to fill the mold, and thus more clamp tonnage to hold the mold closed. 43 to 44. The required force can also be determined by the material used and the size of the part. Larger parts require higher clamping force.
Mould.
mould or die are the common terms used to describe the tool used to produce plastic parts in moulding. Since moulds have been expensive to manufacture, they were usually only used in mass production where thousands of parts were being produced. Typical moulds are constructed from hardened steel, pre-hardened steel, aluminum, and/or beryllium copper alloy 176. The choice of material to build a mould from is primarily one of economics. In general, steel moulds cost more to construct, but their longer lifespan will offset the higher initial cost over a higher number of parts made before wearing out. Pre-hardened steel moulds are less wear-resistant and are used for lower volume requirements or larger components. Their typical steel hardness is 38 to 45 on the Rockwell C scale. Hardened steel moulds are heat-treated after machining. These are by far the superior in terms of wear resistance and lifespan. Typical hardness ranges between 50 and 60 Rockwell C, HRC. Aluminum moulds can cost substantially less, and when designed and machined with modern computerized equipment can be economical for molding tens or even hundreds of thousands of parts. Beryllium copper is used in areas of the mold that require fast heat removal or areas that see the most shear heat generated. 176. The molds can be manufactured either by CNC machining or by using electrical discharge machining processes.
Mold design.
The mold consists of two primary components, the injection mold, A plate, and the ejector mold, B plate. Plastic resin enters the mold through a sprue or gate in the injection mold. The sprue bushing is to seal tightly against the nozzle of the injection barrel of the molding machine and to allow molten plastic to flow from the barrel into the mold, also known as the cavity. 141. The sprue bushing directs the molten plastic to the cavity images through channels that are machined into the faces of the A and B plates. These channels allow plastic to run along them, so they are referred to as runners. 142. The molten plastic flows through the runner and enters one or more specialized gates and into the cavity. 15. Geometry to form the desired part. The amount of resin required to fill the sprue, runner and cavities of a mold is a shot. Trapped air in the mold can escape through air vents that are ground into the parting line of the mold. If the trapped air is not allowed to escape, it is compressed by the pressure of the incoming material and squeezed into the corners of the cavity, where it prevents filling and can also cause other defects. The air can even become so compressed that it ignites and burns the surrounding plastic material. 147. To allow for removal of the molded part from the mold features must not overhang one another in the direction that the mold opens, unless parts of the mold are designed to move from between such overhangs when the mold opens, utilizing components called lifters. Sides of the part that appear parallel with the direction of draw, the axis of the chord position, hole, or insert is parallel to the up and down movement of the mold as it opens and closes. 406 are typically angled slightly, with draft, to ease release of the part from the mold. Insufficient draft can cause deformation or damage. The draft required for mold release is primarily dependent on the depth of the cavity. The deeper the cavity, the more draft necessary. Shrinkage must also be taken into account when determining the draft required. 332. If the skin is too thin, then the molded part will tend to shrink onto the cores that form while cooling and cling to those cores, or the part may warp, twist, blister or crack when the cavity is pulled away. 47. A mold is usually designed so that the molded part reliably remains on the ejector, B, side of the mold when it opens, and draws the runner and the sprue out of the A side along with the parts. The part then falls freely when ejected from the B side. Tunnel gates, also known as submarine or mold gates, are located below the parting line or mold surface. An opening is machined into the surface of the mold on the parting line. The molded part is cut, by the mold, from the runner system on ejection from the mold. 288 ejector pins, also known as knockout pins, are circular pins placed in either half of the mold, usually the ejector half, which push the finished molded product, or runner system out of a mold. 143. The standard method of cooling is passing a coolant, usually water, through a series of holes drilled through the mold plates and connected by hoses to form a continuous pathway. The coolant absorbs heat from the mold, which has absorbed heat from the hot plastic, and keeps the mold at a proper temperature to solidify the plastic at the most efficient rate 86. To ease maintenance and venting, cavities and cores are divided into pieces, called inserts, and sub-assemblies, also called inserts, blocks, or chase blocks. By substituting interchangeable inserts, one mold may make several variations of the same part. More complex parts are formed using more complex molds. These may have sections called slides, that move into a cavity perpendicular to the draw direction, to form overhanging part features. When the mold is opened, the slides are pulled away from the plastic part by using stationary angle pins on the stationary mold half. These pins enter a slot in the slides and cause the slides to move backward when the moving half of the mold opens. The part is then ejected and the mold closes. The closing action of the mold causes the slides to move forward along the angle pins 268. Some molds allow previously molded parts to be reinserted to allow a new plastic layer to form around the first part. This is often referred to as overmolding. This system can allow for production of one-piece tires and wheels. Two-shot or multi-shot molds are designed to overmold within a single molding cycle and must be processed on specialized injection molding machines with two or more injection units. In the first step, the base color material is molded into a basic shape, which contains spaces for the second shot. Then the second material, a different color, is injection molded into those spaces. Push buttons and keys, for instance, made by this process have markings that cannot wear off, and remain legible with heavy use 174. A mold can produce several copies of the same parts in a single shot. The number of impressions in the mold of that part is often incorrectly referred to as cavitation. A tool with one impression will often be called a single impression, cavity. Mold 398. A mold with two or more cavities of the same parts will likely be referred to as multiple impression, cavity. Mold 262. Some extremely high production volume molds, like those for bottle caps, can have over 128 cavities. In some cases multiple cavity tooling will mold a series of different parts in the same tool. Some tool makers call these molds family molds as all the parts are related. Examples include Plastic Model Kits 114.
Mold storage.
Manufacturers go to great lengths to protect custom molds due to their high average costs. The perfect temperature and humidity level is maintained to ensure the longest possible lifespan for each custom mold. Custom molds, such as those used for rubber injection molding, are stored in temperature and humidity-controlled environments to prevent warping.
Tool materials.
Tool steel or beryllium copper are often used. Mild steel, aluminum, nickel or epoxy are suitable only for prototype or very short production runs. Modern hard aluminum, 7075 and 2024 alloys, with proper mold design, can easily make molds capable of 100,000 or more part life with proper mold maintenance.
Machining.
Molds are built through two main methods, standard machining and EDM. Standard machining, in its conventional form, has historically been the method of building injection molds. With technological development, CNC machining became the predominant means of making more complex molds with more accurate mold details in less time than traditional methods. The electrical discharge machining, EDM, or spark erosion process has become widely used in mold making. As well as allowing the formation of shapes that are difficult to machine, the process allows pre-hardened molds to be shaped so that no heat treatment is required. Changes to a hardened mold by conventional drilling and milling normally require annealing to soften the mold, followed by heat treatment to harden it again. EDM is a simple process in which a shaped electrode, usually made of copper or graphite, is very slowly lowered onto the mold surface, over a period of many hours, which is immersed in paraffin oil, kerosene. A voltage applied between tool and mold causes spark erosion of the mold surface in the inverse shape of the electrode.
Cost.
The cost of manufacturing molds depends on a very large set of factors ranging from number of cavities, size of the parts, and therefore the mold, complexity of the pieces, expected tool longevity, surface finishes and many others. The initial cost is great, however the per-piece cost is low, so with greater quantities the unit price decreases. Rubber injection molding process produces a high yield of durable products, making it the most efficient and cost-effective method of molding. Consistent vulcanization processes involving precise temperature control significantly reduces all waste material.
Injection process.
With injection molding, granular plastic is fed by gravity from a hopper into a heated barrel. As the granules are slowly moved forward by a screw-type plunger, the plastic is forced into a heated chamber, where it is melted. As the plunger advances, the melted plastic is forced through a nozzle that rests against the mold, allowing it to enter the mold cavity through a gate and runner system. The mold remains cold so the plastic solidifies almost as soon as the mold is filled.
Injection molding cycle.
The sequence of events during the injection mold of a plastic part is called the injection molding cycle. The cycle begins when the mold closes, followed by the injection of the polymer into the mold cavity. Once the cavity is filled, a holding pressure is maintained to compensate for material shrinkage. In the next step, the screw turns, feeding the next shot to the front screw. This causes the screw to retract as the next shot is prepared. Once the part is sufficiently cool, the mold opens and the part is ejected. 13.
Different types of injection molding processes.
Although most injection molding processes are covered by the conventional process description above, there are several important molding variations including, but not limited to, die casting, metal injection molding, thin wall injection molding of liquid silicone rubber, 17 to 18. A more comprehensive list of injection molding processes may be found here.
Process troubleshooting.
Like all industrial processes, injection molding can produce flawed parts. In the field of injection molding, troubleshooting is often performed by examining defective parts for specific defects and addressing these defects with the design of the mold or the characteristics of the process itself. Trials are often performed before full production runs in an effort to predict defects and determine the appropriate specifications to use in the injection process. 180. When filling a new or unfamiliar mold for the first time, where shot size for that mold is unknown, a technician tool setter may perform a trial run before a full production run. He starts with a small shot weight and fills gradually until the mold is 95 to 99% full. Once this is achieved, a small amount of holding pressure will be applied and holding time increased until gate freeze-off, solidification time, has occurred. Gate freeze-off time can be determined by increasing the hold time, and then weighing the part. When the weight of the part does not change, we then know that the gate has frozen and no more material is injected into the part. Gate solidification time is important, as it determines cycle time and the quality and consistency of the product, which itself is an important issue in the economics of the production process. Holding pressure is increased until the parts are free of sinks and part weight has been achieved.
Molding defects.
Injection molding is a complex technology with possible production problems. They can be caused either by defects in the molds, or more often by the molding process itself. 47 to 85. Methods such as industrial CT scanning can help with finding these defects externally as well as internally.
Tolerances and surfaces.
Molding tolerance is a specified allowance on the deviation in parameters such as dimensions, weights, shapes, or angles, etc. To maximize control in setting tolerances, there is usually a minimum and maximum limit on thickness. Based on the process used, 439 injection molding typically is capable of tolerances equivalent to an IT grade of about 9 to 14. The possible tolerance of a thermoplastic or a thermoset is plus minus 0.200 to plus minus 0.500 mm. In specialized applications, tolerances as low as plus minus 5 on both diameters and linear features are achieved in mass production. Surface finishes of 0.0500 to 0.1000 or more better can be obtained. Rough or pebbled surfaces are also possible.
Power requirements.
The power required for this process of injection molding depends on many things and varies between materials used. Manufacturing Processes Reference Guide states that the power requirements depend on a material's specific gravity, melting point, thermal conductivity, part size, and molding rate. Below is a table from page 243 of the same reference as previously mentioned that best illustrates the characteristics relevant to the power required for the most commonly used materials.
Robotic molding.
Automation means that the smaller size of parts permits a mobile inspection system to examine multiple parts more quickly. In addition to mounting inspection systems on automatic devices, multiple-axis robots can remove parts from the mold and position them for further processes. Specific instances include removing of parts from the mold immediately after the parts are created, as well as applying machine vision systems. A robot grips the part after the ejector pins have been extended to free the part from the mold. It then moves them into either a holding location or directly onto an inspection system. The choice depends upon the type of product, as well as the general layout of the manufacturing equipment. Vision systems mounted on robots have greatly enhanced quality control for insert molded parts. A mobile robot can more precisely determine the placement accuracy of the metal component, and inspect faster than a human can.
Gallery.